So our last unit is on electrochemistry. And basically what we're going to be taking a look at is redox reactions. So we've kind of put these on the back burner all year. Now it is time to take a look at them. So redox reactions or electrochemistry is all about movement of electrons or electron transfer. So these reactions are called oxidation reduction reactions, or for short, they call them redox reactions. In redox reactions, you've got movement of electrons. And this field is often called electrochemistry because the electrons create an electric current when they move, or they require an electric current in order to get them moved. So there's spontaneous redox reactions and there's non-spontaneous redox reactions. If they're spontaneous, they're going to cause an electric current, so you can use them like a battery. If they require an electric current to get those electrons to move, obviously that's not spontaneous. That's it's using an outside source in order to get the energy to move those electrons, but you can still accomplish things. For example, electroplating is an example of a situation where you run a current through something and you coat an object with a certain kind of metal. So electrochemical processes are all oxidation and reduction processes. The energy is released if it's a spontaneous reaction and it's converted into electricity, or like we said before, electrical energy is used in order to cause a reaction to occur. So here's an example of a redox reaction. How do you know it's a redox reaction? You've got to look and see that species are changing charge. One thing's going to be losing electrons, another thing's going to be gaining electrons. So starting off, we've got magnesium metal. So magnesium metal is going to have no charge at all. Likewise, oxygen gas has no charge. They are atoms, not ions. But when they react to make magnesium oxide, magnesium's +2 and oxide is -2, so you have movement of electrons. Magnesium is losing 2 electrons and going to Mg2+. Oxygen is gaining 2 electrons and going to O2-. So you can write what's referred to as half reactions. So a half reaction involves half of the reaction. Either it's the oxidation half reaction or it's the reduction half reaction, and we'll get into definitions momentarily. But basically we're taking magnesium and making magnesium 2+. So in order to write this half reaction, we're going to start with just kind of showing the skeleton. Mg to Mg2+ is what we're doing, but we want to make sure that we maintain a balance. So we balance the atoms, so 2 magnesiums to 2 magnesium 2+. Since each of these magnesiums lose 2 electrons, there's a total of 4 electrons being lost. So we want to show that as well. So when you write a half reaction, you show the atoms balancing, but you also have to show the electrons and you have to show charge balancing. In order to balance charge, the total charge on the left has to equal the total charge on the right. So on the left side, I've got 2 magnesiums, 0 charge, so 0 on this side. 2 + 2, so that's a total of +4. And a total of -4, so I add those together, and it's still 0 on both sides. So the other half reaction is the oxygen half reaction. So O2 is going to be gaining 2 electrons to become O2-. And again, because there's 2 atoms involved, a total of 4 electrons are going to be gained. Again, if you take a look at the balancing, atoms are balanced. I've got 2 oxygens on one side, and I've got 2 on the other. Total of -4 on the reactant side. Total of -4 on the product side, so it is balanced. Balancing doesn't mean you have to have a charge of 0. Balancing half reactions means you have to have the same charge on both sides. So when substances lose electrons, that's called oxidation. When substances gain electrons, that's called reduction. So magnesium is undergoing oxidation and oxygen is undergoing reduction. So some terminology, like I said, oxidation is the loss of electrons. It's also the increase in oxidation number, but we haven't talked about what those are yet. So loss of electrons is oxidation. Gain electrons is reduction, but you can also see that reduction is the decrease in oxidation number. Again, we'll take a look at oxidation numbers a little later. Two other terms, the oxidizing agent, the oxidant, is the electron acceptor. It's the thing that's gaining the electrons, which means it's the substance being reduced. So the oxidizing agent is causing oxidation, but it's causing oxidation because it's accepting the electrons from the thing that's losing them. So think of the agent. You know, you've seen, you've heard of a travel agent. A travel agent isn't doing the traveling. A travel agent is helping you travel. So the oxidizing agent isn't being oxidized. The oxidizing agent is helping something else get oxidized. So the oxidizing agent gets reduced, and therefore the reducing agent gets oxidized. It's the thing accepting the electrons, so it's becoming more negative. It's being reduced. So these terms are going to crop up now and again, so it's important that you remember the difference. These two you'll know down pat. All right, so a couple different ways that you can remember things. Reduction can happen. Reduction can't happen without, I'm not reading right. Reduction, or the gain of electrons, can't happen without oxidation to provide electrons. So you can't have one without the other. So two ways to remember it. You can remember Leo the lion says grr. So you've got loss of electrons is oxidation, gain of electrons is reduction, and Leo says grr. So that's one way that you can remember it. You can also remember oil rig. Oxidation is lost, reduction is gain. So you're an animal fan or you're a race car fan, I don't know. But two ways that you can remember what oxidation is and what reduction is. All right, so I said we'd take a look at oxidation numbers. This is going to take a little bit of time to get used to. Oxidation numbers are not necessarily the same as charge. Sometimes the oxidation number is the same as the charge, but not always. So there's a lot of rules to deal with. We're going to practice this. Plenty of problems to practice. We'll do those in class. All right, so the oxidation number is the charge that the atom would have in a molecule if electrons were completely transferred. Oxidation numbers are not real. They are hypotheticals that scientists assign just to try and keep track of how electrons are moving. So again, oxidation numbers are not real. Oxidation numbers are made up numbers that chemists use to track electron movement. Sometimes they represent the charge of the ion, but not always. Oxidation occurs when the oxidation number of the species increases. So oxidation increases because it's gaining electrons. So the oxidation number is kind of controlling or kind of giving you a picture of where the electrons are moving. Numbers go up when electrons are gained. Numbers go down when electrons are lost. And like I said, reduction occurs when the species loses the electrons. Okay, so some rules. And these are guidelines because you got things that kind of compete against each other sometimes, but for the most part, they're pretty good. If you have free elements in their uncombined state, they have an oxidation number of 0. So notice they can be a molecule, but the way they're normally found, they're going to have an oxidation number of 0. Okay? So elements, molecules that represent the elements, all 0. That one's easy. Rule number 2. Monatomic ions, the oxidation number is equal to the charge. So Li plus is +1. Fe3 plus is +3. O2 minus is -2. So that's easy. Individual single atom ions have the oxidation number equal to their charge. Oxidation number of oxygen is usually -2. Even if it's in a molecular substance, it's usually -2. The one exception is if you have a peroxide. In peroxides, you wind up with oxygen being -1. You have 2 of them, so H is +1. Oxygen normally is -2, but in order to balance them out, since you have 2 oxygens, each oxygen only needs a -1 charge. So you don't see peroxides often, but occasionally you'll see peroxides. The oxidation number for hydrogen is +1. Okay, so that's how I knew that we were looking at a peroxide. Oxidation numbers for hydrogen are +1, except when they are bonded to metals in binary compounds. So in these cases, then the oxidation number is +1. So lithium goes +1, which means hydrogen has to be -1 in this case. So if you have hydrides, lithium hydride, calcium hydride, anything like that, any hydride, hydrogen is going to have a -1 charge as opposed to a +1 charge. Group 1A metals are always +1. Group 2A metals are always +2. Fluorine is always -1. Fluorine, being the most electronegative, is always going to get the electron, so it's always going to be -1. It's not always true with the rest of the halogens. They are not always -1. Another thing, the sum of the oxidation numbers of all the atoms in the molecular ion have to equal the overall charge. So that's one thing that's going to help you figure it out. So you know oxygen is -2 and you know hydrogen's +1. You can figure out carbon in bicarbonate with that idea. Here's the example. So what's the oxidation number of all the atoms? Well, we know that hydrogen's +1. We know that oxygen is -2. So now you got to think about it. Oxygen is -2. I have 3 of them. So that's a total of -6. Okay, 3 times 2 is -6. Hydrogen is +1, and then plus carbon, whatever carbon's oxidation number is, all have to add up to -3. So -6, -3, -1. -6 plus 1 is -5. I need an overall charge of -1, which means carbon must have an oxidation number of 4 plus. So that's how you do oxidation numbers. We're going to practice a little bit, and I think we might need to practice, or we'll give you the answers in the next video. So, oh, shoot. Okay. We're doing one at a time. So we'll start these and probably continue them in the next video unless we run out of time. So sodium's +1, which means hydrogen in sodium hydride has to be -1. Next one, think about it. Start with oxygen. Each oxygen's -2, which means that's a total of 10. Phosphorus needs to be a total of +10. So oxygen's -10, phosphorus, what charge does it need to be in order to be a total +10? Phosphorus must be +5. Next one, dichromate. Okay, so oxygen is -2, so that's -14. You have to have an overall charge of -2, so this must add up to +14. I'm sorry, +12. So -14. Overall, you have to have -2, which means the chromium has to be total +12. So each chromium must be +6. Next example, tin bromide. Okay, bromine typically is going to be -1. So you've got 4 of them for a total of -4, which means tin is going to be +4. And so that actually agrees with the ionic charges. That makes sense. It's just when you have situations like a polyatomic ion where you don't necessarily know what the charges are going to be. I think there's one more, barium oxide. Okay, barium is always going to be +2. Okay, because it's an alkaline earth metal, which means oxygen has to be total of -2. There's 2 of them, so this is an example of a peroxide. Oxygen is -1 in this case. So there's plenty of problems in your book to practice. And we are going to quit here and pick up half reactions in the next video.